Hi, welcome to the universe of first-order RC circuits. In this video, we will give you a practical and interesting example. The forced response of a first-order RC circuit where there is a voltage source and a switch in series with a resistor and a capacitor. The switch, K, is initially opened, ensuring that the capacitor current, IC, is zero, and its voltage, UC, remains constant. The capacitor is completely discharged at time zero. At that instant, the switch, K, is closed and remains closed from that moment on. We want to know what happens to the voltage and the current from that instant onwards, that is, for t equal or greater than 0. In here, you'll find math formulas, some illustrations, and graphs so you can pause the video whenever you need a little bit more time to let the information sink in. But let's get down to business. In a circuit with such initial conditions, we have a voltage U equals E for t equal or greater than 0. The equation of the circuit is as follows. In case you want to remember how to get here, you can watch our introduction video to first-order RC circuits. Alright, knowing the value of U, which is E, we can replace it in this equation. Then, to determine the voltage across the capacitor for t equal or greater than 0, we need to solve this first-order ordinary differential equation. First order because it has only the first derivative of one dependent variable UC with respect to an independent variable t. In this equation, E, R, and C are constants, and UC is the unknown. The solution to this equation is the following expression. The demonstration process of how to get to this solution is available in the second video on the Laplace transform, regarding, of course, RC circuits. We can also determine the current through the capacitor, which is exactly the same across the source and the resistor for t equal or greater than 0, which is given by this equation. But how do we get to it? Well, it's easy actually, through the equations that we went through before. The current through the capacitor and resistor can be determined by the famous Ohm's law that you probably know like the back of your hand. IR equals UR divided by R. In the circuit, the voltage across the resistor is given by UR equals U minus UC, in which, according to the initial conditions already referred, U equals E. So, the voltage across the resistor equals E minus UC. Ultimately, by replacing UC with the equation we saw above, this one, we get our final expression, which is this one. Cutting things short, these are the equations that translate the forced response of a first-order RC circuit. But now, let's analyze the graphic representations of these expressions. After a time equaling R times C, the voltage across the capacitor terminals, initially discharged, reaches 63.2% of the value E. This time period, R times C, is called time constant, which is represented by the letter tau. After 3 times that time, that is, after 3 times tau, the voltage across the capacitor reaches 95% of E, and after 5 times tau, it reaches 99.3% of E. On the other hand, the IC current through the capacitor behaves in the following way. For the instant t equals tau, the IC current reaches 36.8% of its initial value, E divided by R. At the instant t equals 3 times tau, IC reaches 4.9% of its initial value, and at the instant t equals 5 times tau, IC reaches 0.7% of its initial value. In conclusion, we can see that the initial value of UC of 0 equals 0, and the initial value of IC of 0 equals E divided by R. We can also see that as t tends to infinity, the voltage across the capacitor UC approaches its steady state, which is E. And also that as t tends to infinity, the current through the capacitor IC approaches its steady state, which is 0, showing that IC only has transient state. But let's take a look at another situation. If the switch K is closed at an instant t equal to t0 instead of at time 0, we use the same line of thought, with only a few twitches. The voltage on the capacitor will be defined by this expression, and the current through the capacitor by this one. Therefore, the graphs obtained will be the following, where it is shown that the capacitor begins to charge only from the moment t0 instead of at time 0. In the next video, we'll show you the total response of a first-order RC circuit, so stay tuned. See ya!